Okay, so in this video, we're going to be going over the 2001 AB Calculus exam. So without further ado, let's get started with question number 1. So we have these two equations, y is equal to tangent of x, and y is equal to 2 minus x squared, or x cubed. And then we have this region R, it's like triangle looking thing here. And then we have this region S. I don't know what it looks like, semicircle-ish thing. And then, so part A asks us to find the area of R. Okay, so an important first step in this is this intersection point. This point here, the coordinates of this point are going to be critical when it comes to solving this problem. Okay, so let's figure out what we can do here. So, what we can do is, to find the intersection point, we're going to set this curve equal to this curve, and that's going to happen at this point. So we'll set 2 minus x cubed equal to tangent of x. And by the way, this stuff that we're doing here, we're going to use this in all of the parts. This isn't specifically for part A. This is like the preliminary work that we're going to need later in the road. So now that we set these two equal to each other, if you graph this, I can graph this in y1, and I can graph this in y2, and that's going to give me x is equal to approximately 0.9. And then if I want to find the y coordinate, I can take the tangent of it, and I'm going to get y is approximately 1.27. Now I don't want to use these approximate values for the rest of the problem, because that's going to lead to some small inaccuracies that are not going to give you full credit. So the way we're going to preserve the accuracy of these values is we're going to store them as variables in our calculator. So what we'll do is we'll store this as A, and we'll store this as B. What that means is anytime down the road, if we want to use the x intersection point, I'll just use the variable A, and if I want to use the y intersection point, I'll use the variable B. You can use any variables you want, those are just the ones I prefer. And then let's just label this. So at this intersection point, the x coordinate is A, and the y coordinate is B. Okay, with that down the road, or with that out of the way, let's get started on the rest of the problem. I'll erase this as well. Alright, so let's get started on the actual problem. Find the area of R. So notice that we don't have like a top curve and a bottom curve. We have a left curve and a right curve. So when you see something like that, you know that we're going to be dealing with everything in terms of y. So we'll take these two equations and solve them for x. So everything else will be in terms of y. When we have y is equal to tangent of x, if we solve that for x, that's going to give us that x is the inverse tangent of y. And then when we have y is 2 minus x cubed, I can add x cubed to both sides, subtract y from both sides. I'll get x cubed is 2 minus y, and then x is 2 minus y to the 1/3 power. Okay, and then now that we got those two equations set, we can start with finding the actual area. So what we're going to do now is we're going to find the radii, the two different radii here. The first radii, the small radius, is going to go from here to the first curve, and the big radius is going to go from here to the second curve like that. And then now we need to find the equation that represent these two radii. And then for the small one, it's going to go from x equals 0 to x equals this first graph. Well, this first graph is y equals tangent of x. So from 0 to this is going to be from 0 to the x coordinate, which is the inverse tangent of y. So we're going from 0 to the inverse tangent of y. So this distance is just the inverse tangent of y. Alright, that little r is the inverse tangent of y. And by that same logic, going from 0 to this other curve, I can say that big R is 2 minus y to the 1/3, because that's what we got over here for this x coordinate as a function of y. So now that we have our two radii, we can use the equation for area, which is the integral from 0 to the intersection point of big R squared minus little r squared. And in this case, since we're dealing with y, so it'll be dy. And then now the question is, what's the intersection point? Well, since we're going from this to here, this is like the range of the values that we want to use. We're going from 0 to b, right? We're integrating all of this distance up until b. So we're going from 0 to b. And then we know our big R is 2 minus y to the 1/3. And then we know our little r, the inverse tangent of y, dy. And then you put this in the calculator, and you're going to get approximately 0.729. And that is our final answer. Okay, so for points, you'd get 1 point for the correct bounds of 0 and b. It's okay to use the variable b as long as you defined what it is earlier in the problem. And then this integrand will get you another point, and the third point for the correct answer of 0.729. And also get the very similar part b. Okay, so part b, thankfully this is a bit easier than part a. We need to find the area of this region S. And now since we do have a top curve and a bottom curve, we can do everything in terms of x. We don't have to manipulate the equations like we did before. Okay, so what we're going to do is we're going to say, alright, this is my top curve, so this is my big radius, and my little radius is this distance. Now we need to find these values. So little r goes from y equals 0 to y equals tangent of x, so this distance is tangent of x. And then my big R goes from y equals 0 to y equals 2 minus x cubed, so the distance is 2 minus x cubed. And then now for the bounds of integration, again we're starting at 0, and what are we going to? Well, we're going out until we reach this distance a, right? We're integrating from 0 to a. So 0 to a, and then now it's just going to be the same thing, big R minus little r. Our big R is 2 minus x cubed, and then our little r is tangent of x, put a dx on there, and then this is going to be approximately 1.161 if evaluated in the calculator. And again, this is going to be a 3-point question, 1 point for the bounds, 1 point for the integrand, and 1 point for the answer. Now let's look at part C of this question. So now we need to find the volume of the solid generated when S is revolved about the x-axis. Okay, let me I think you remember what those are by now. So we need to revolve S around the x-axis, right? Let's rewrite our radii because those are kind of important. We have this, our little r, being tangent of x, and then this being our big R, which is 2 minus x cubed. And then since we're revolving it around the x-axis, these are the radii that we want, right? Because it's touching the x-axis. And then now we have the radii, we just need to employ a slightly different formula for revolving. So the formula is pi times the integral from, well, we're starting at 0, and we're going to a. Remember, this is a. And it comes from 0 to a. And then instead of saying big R minus little r, it's big R squared minus little r squared dx. So now again, it's just a matter of plugging in numbers. So we have pi times the integral from 0 to a of big R, so 2 minus x cubed squared, minus tangent of x squared, or as we like to write it, tangent squared of x dx. And then again, if you evaluate this out, you're going to get 2.652 pi. Okay, so for points, again, it's going to be 1 point for the limits of integration, or the bounds of integration, and your pi in the front, another point for this integrand, and a third point for the correct answer. That was the conclusion of question 1. Now let's move on to question number 2. Okay, so for question 2, we have the temperature of a pond being the differentiable function w of t, and then we have the table that's giving us the water temperature every 3 days over a 15-day period from 0 to 15. So for part A, we need to use the data from the table to find an approximation for w prime of 12, include units of measure. Okay, So there's a bunch of different variations of the way you could do this. You're going to get slightly different answers depending on which way you choose. But as long as your method is sound and you have correct math, then you'll get the full points. I'm just going to show you the way that I would have done it. Okay, so to find an approximation for w prime of 12, we need to look at the average rate of change between two values on the chart. You could use any two values. I think the most accurate way would be using 9 and 15. And the theory is that if we take the average rate of change between 9 and 15, since 12 is right in the middle, this approximation of the average rate of change is going to be a pretty good approximation of the instantaneous rate of change at 12, or w prime of 12, which is what we want, right? So the way we're going to do this is to find the average rate of change between 9 and 15. That's going to be w of 15 minus w of 9 over 15 minus 9. I don't know if you can hear people in my family talking. I'm sorry if you can. Anyways, so this is, remember, this is what this is an approximation for w prime of 12, right? We're approximating the instantaneous rate of change of 12 as a average rate of change between 9 and 15. So now what is this? Well, looking at the table here, looks like for w of t, w of 15 is 21, and w of 9 is 24. So instead of w of 15, I'll replace it with 21. Instead of w of 9, I'll replace that with 24. And then over 15 minus 9. So this is my approximation for the instantaneous rate of change. And in terms of units, so the units for the derivative is going to be the units for w divided by the units for t. Because if we were to graph this, for example, we'd have t on the x-axis and w of t on the y-axis, and the units for the derivative are the units for the y-axis over the units for the x-axis. So the units for w are degrees Celsius, the units for x-axis are days, so the units for the derivative are going to be degrees Celsius over days, or degrees Celsius per day, which makes sense, because we're trying to find out how many degrees, how much the temperature is changing as a function of time, right? So it's degrees Celsius per day. Okay, so that was a 2-point question, 1 point for the approximation and 1 point for the answer. Remember, if you got a slightly different number than this, it's cool as long as you did the same steps. Okay, now let's look at part B of this question. Okay, so now we need to approximate the average temperature over the interval 0 to 15 using a trapezoidal approximation with delta t is equal to 3 days. Alright, so what do we do here? So we have a trapezoidal approximation and we have an equal base length, right? Our base length is 3. Right here it says. So we need to use the formula for a trapezoidal approximation with an equal base. And what that is, it's 1/2 times the base, the common base, times the first height, times 2 times the second height, 2 times the third height, and so on until you get to 1 times the nth height, which is the final height. Alright, so now since we're going in terms of 3, this is going to be our first height, this is going to be our second height, third, fourth, fifth, and sixth. Right? And then our base, our common base, is going to be the delta 3, which is 3 days. So now we can just plug in this stuff. So we'll get 1/2 times 3 times h1 is 20, h2 is 31, 28, 24, or 2 times 24, my bad, plus 2 times 22, plus 21. And then if you were to put this in your calculator, you would get 376.5. And let's think about what this really is. The trapezoidal sum is a way to approximate an integral, right? So when we took the trapezoidal sum from 0 to 15, we were approximating the integral of w from 0 to 15. So what this is this is an approximation of the integral from 0 to 15, because we went from t equals 0 to t equals 15 of w of t. So now let's look at what the question was really asking, because they didn't want just the trapezoidal sum. they wanted the average temperature from 0 to 15. And the formula for the average temperature, or the average value of a function, is 1 over b minus a times the integral from a to b of f of x dx. And then in our case, we started at time t equals 0, we went to time t equals 15, so we'd have 1 over 15 minus 0, or 15, times integral from 0 to 15, or function is w of t. Right? This is the average value, or the average temperature on 0 to 15. And then how do we figure out what this integral is? Well, remember up here, we got an approximation for the integral. This 376.5 is the approximation of the integral from 0 to 15. So I can plug that in here, and then that'll get me 1 over 15 times 376.5. And then the units for this are going to be, since this is the average temperature after all, the units for this is going to be the same as the units for temperature. And the units for temperature is degrees Celsius, so the units for the average temperature is also in degrees Celsius. And then for units, or for points, you'd get 1 point for the trapezoidal sum, and the second point for the average temperature. Okay, now let's look at part C. Okay, so part C, we have the function P, given by that stuff, as a model for the temperature of the pond, or the temperature of the water in the pond at time t, where t is in days and p of t is in degrees Celsius. Find p prime of 12. Okay, so let's take the derivative of this function to find p prime of x, and then plug in 12 to get p prime of 12. And that's a pretty straightforward way to solve the problem, I think. So let's just find p prime of t. And I think a general strategy is when they're asking you for like the specific value, just take the general derivative first and then plug in your value, just to like eliminate any extra confusion. So the derivative of this, that's going to be gone because that's a constant. And then for this thing, we have to use the product rule. So we'll have 10 e to the negative t over 3 times the derivative of t, which is 1, plus 10t times e to the negative t over 3 times the derivative of negative t over 3, which is negative 1/3 by the chain rule. So this is p prime of t. And now, since we want p prime of 12, all we have to do is plug in 12 into here. So it's 10 times e to the negative 12 over 3 plus 10 times 12 times e to the negative 12 over 3 times negative 1 over 3, like that. Right, there's no need to simplify any of this. Don't waste your time. If you did simplify it, you'd get negative 30 e to the negative 4, but again, there's no point bothering. And then for units, they want us to explain the meaning of your answer in terms of water temperature. So remember how the derivative is the rate of change of something? So since p of t is the temperature, p prime of t is the rate of change of the temperature, and p prime of 12 is going to be the rate of change of temperature at time t equals 12. And even though you don't have to evaluate this numerically, you should be able to see that this is a negative value. So what we can say is that at time t equals 12, the water temperature is decreasing at a rate of this. Let me just copy, paste. So the average, or the temperature of the water is decreasing at a rate of the absolute value of this, right? Since this is how much this is negative, we can say it's decreasing at a rate of the absolute value of this. And the units for that is going to be, like we said in part A, it's going to be degrees Celsius per day. Okay, and just to explain that explanation a little bit further, we said the water temperature is changing, and then since it's negative, we're going to say the water temperature is decreasing, and then for the rate at which it's decreasing at the absolute value of this. since we already said decreasing, we already covered the negative part of it, and we can put an absolute value now. Okay, so that was part C. For units, this should just be a quick 1 point question, or no, it's actually 2 points, sorry. 1 point for taking the derivative correctly, and the second point for the correct explanation that the water temperature is decreasing at t equals 12 days. Now let's look at part D. Okay, so part D, use the function p defined in part C to find the average value of p of t from 0 to 15. Okay, so remember the average value function is 1 over b minus a times the integral from a to b of f of x dx. And then we're going from 0 to 15, so a is 0 and b is 15. And then our f of x is our w of t, right? So 1 over 15 minus 0 times the integral from 0 to 15 of w of t. Instead of w of t, I'm actually going to say p of t, because we have an actual like concrete function we can plug in. So p of t, remember p of t and w of t, those are both like the temperature as a function of time, the same thing. D, not dx, dt. So this is the average temperature from 0 to 15. And then since I have like an actual number for p of t, I can take this and plug it into the p of t function. So this is 1 over 15 times the integral from 0 to 15 of the stuff we had there, 20 plus 10 t e to the negative t over 3 dt. And you really can't do this by hand unless you're in BC, because this would require integration by parts. But you can just use a calculator, plug it in, and you're going to get 25.757. And then for the units for this, again, this is average temperature. So the units for this are going to be the same as the units for temperature, so degrees Celsius. And as for points, this is a 3-point question. 1 point for including the 1 over 15 and the bounds from 0 to 15. Another point for taking the value of p of t, which is this stuff, and plugging it into the integral. And then the 3rd point for the correct answer. That was question 2. Now let's look at question number 3. Question number 3. So we have a car traveling on a straight road with the initial velocity 55 feet per second. And then for 0 to 18, the car's acceleration is the piecewise linear function defined by the graph above. So before we even start, let's think about the relationship between the velocity of the car and the acceleration of the car. Well, you should know from your particle motion that if you take the derivative of velocity, you're going to get the acceleration. And then likewise, if you take the integral of acceleration, you're going to get velocity. So now that we got those two relationships out of the way, let's look at part A of this question. Is the velocity increasing at time t equals 2 seconds? Why or why not? So if the velocity of the car is increasing, you should know that if the velocity is increasing, then its derivative is positive. Okay, so if the derivative of velocity is positive at time t equals 2 seconds, then its velocity is increasing. So is v prime of 2 positive? If so, then v of 2 is increasing. And well, isn't v prime of 2 equal to a of 2? So I can rephrase this question as, is a of 2 positive? And then is a of 2 positive? That's a really simple question that we can just answer by looking at this graph. So we have acceleration as a function of time. If we go to time t equals 2, we see that a of 2 is 15, which is definitely greater than 0. So since a of 2 is greater than 0, it's 15, that means v prime of 2 is greater than 0. That means the velocity is increasing at time t equals 2. For your explanation, since they're asking why or why not, you have to say, well, the velocity is increasing at time t equals 2 since a of 2 is greater than 0. and it's good to use a of t and not v prime of t, because the velocity is not given to us. We're not explicitly given the formula for v of t, so it's best to not use v and use a instead in your explanation. Just as a 1 point question, just 1 point for getting the right answer. Now let's look at part B. Part B asks, at what time in the interval 0 is less than equal to t is less than equal to 18, other than t equals 0, is the velocity of the car 55 feet per second, and why? So if the velocity of the car is 55 feet per second, remember that was the initial velocity? If the velocity of the car is 55 feet per second, that means that the change in velocity was 0. Okay, and then remember that the change in velocity is given by the integral of acceleration. So what this means is that the integral of acceleration is 0. If the integral of acceleration is 0, then the change in velocity is 0. And then that means it would have the same initial velocity of 55 feet per second. Okay, and then the integral of acceleration is the final velocity minus the initial velocity, and that equals 0, which would mean that the final velocity equals the initial velocity, right? That's what we want. And then to find out when is the acceleration integral 0, well, since the integral is the area under the curve, if you want this integral to be 0, then we have to find out when is the area under the curve 0. So let's look at this graph, and we have this positive rectangle, then we have this positive triangle, and then we have this negative triangle, and we have this negative rectangle. And then since this cancels with this cancels with this, from 0 to 12, the total area under this acceleration graph is 0, right? Because this is positive and this is negative, and they're going to cancel out. So since they cancel out, the total area is going to be 0, like we wanted here. So what that means is the integral from 0 to 12 of a of t is 0. I forgot the dt is 0, and then this means that v of 12 minus v of 0 is 0, and adding v of 0 to both sides, I get v of 12 is v of 0, which is, since v of 0 is 55, this is 55. So the time that the velocity is 55 is at time t equals 12, because that's when the total area under the curve is 0. And it looks like from 12 to 18, it's never going to be 0 again, because this is like getting negative, and then 18, it doesn't go, it increases, but it doesn't increase all the way to 0 again. So the only time is at time t equals 12, and for your explanation, you'd say that is because the integral of a of t dt from 0 to 12 is 0, which means that the velocity at 12 is the same as the velocity at 0, which is 55. And then you get, for points, you get 1 point for the correct answer of t equals 12 only, and then another point for the proper explanation. Let's get part C. So, part C, on the time interval 0 to 18, what is the car's absolute maximum velocity, and at what time does it occur? So they want the t value and the v of t. So they want both numbers. Okay, so when we're dealing with absolute extrema, it's good to think about where it could possibly occur. So for absolute extrema, what we need to do is we need to check endpoints and critical values. So 1 is endpoints, 2 is critical values. And then, so for our endpoints, that's going to be t equals 0 and t equals 18. And then for our critical values, that's going to be where the acceleration graph crosses the x-axis, or crosses the t-axis. So it's going to be t equals 6 and t equals 16. So these are the 4 possible values for the the absolute maximum, and then let's see if we can eliminate one of these. Okay, so at 0, the velocity is 55, but then notice that the net area is positive from 0 to 6, so it means the velocity is increasing from 0 to 6. So at some point the velocity is greater than 55, so t equals 0 can't be it. Okay, and then it looks like from 0 to 6 we have a positive area, and then from 6 to 16 we have a much bigger negative area. So the net area from 0 to 16 is going to be negative. So at 16 the velocity is going to be less than 55, so that's not the absolute maximum either. Okay, and then for 18, so now we're left with t equals 6 and t equals 18, right? So is the velocity here greater than the velocity here? So is this area from 0 to 6 greater than this area from 0 all the way to 18? And this is really just like a visual thing. You should be able to pretty clearly see that the area from 0 to 6 is greater, because from 0 to 6 it's this, and then from 0 to 18 it's this positive, and then this really, really big negative, and this small positive. So like the net area is obviously going to be greater at t equals 6 than t equals 18. So the absolute maximum is going to occur where the area is greatest, so it's going to occur at t equals 6. Okay, and then they also want the absolute maximum at t equals 6. So at t equals 6, the velocity is the initial velocity plus this net area, right? So plus that integral of acceleration from 0 to 6 of the acceleration. The initial velocity is 55 plus, and then the area under the curve is going to be this rectangle. So 2 times 15, 30, and then this triangle, which is 4 times 15 times 1/2. So it's 4 times 15 is 60. 60 times 1/2 is, well, I'm not even going to waste my thought process on that. Algebra is 1 times 15 times 4. So this is the velocity, the absolute maximum velocity, and it occurs at time t equals 6. So for the explanation, we'll say that, well, we looked at the endpoints, we looked at the critical values, and then we looked at the velocities at each of those points, and we found that at t equals 6 the velocity is the greatest, so therefore it's the absolute maximum velocity at that time. Okay, now let's look at the final part for this question. Okay, so part D, we need to find the times where the velocity is equal to 0, and we need to justify our answer. Okay, so the way we're going to do this is we're going to examine the absolute minimum. Okay, we want to see what the absolute minimum velocity is, and based on there we'll see what we can do. Okay, so the absolute minimum is where this area is the lowest, and then it's pretty clear just looking at the graph that the lowest area happens at the end of this like negative place here at time t equals 16. That's where the net area is the lowest. So we have an absolute minimum at t equals 16. And what is the velocity at 16? Well, v of 16 equals the initial velocity plus the integral from 0 to 16 of of a of t dt. So what's this net area here? Well, we know that the area from 0 to 6, that cancels with the area from 0 to 12. So I'm not even going to bother calculating those. I'm just going to calculate this area from 12 to 16. Okay, and that's going to be this rectangle that has a t value of 2 and an acceleration of -15. So this is 55 plus 2 times negative 15 plus, and this triangle, which is 1/2 times 2 times negative 15. And let's actually like numerically calculate this out. This is 55 minus 30 minus 15, which is 10. And so this is the minimum velocity in from 0 to 18. This is the lowest the velocity is ever going to get. It's never going to get lower than 10. So when the question asks, at what time is the velocity equal to 0? Well, we just said that it's never going to go lower than 10. So obviously it can never go to 0, right? So the answer is it'll never reach 0 because the absolute minimum, which is 10, is greater than 0. Therefore, from 0 is less than or equal to t is less than or equal to 18, the velocity will never equal 0. That's a justification. And then for points, we're gonna have 2 points. You're gonna have 1 point for correctly saying that the velocity is never equal to 0, and then a second point for the proper justification. Okay, now let's move on to question number 4. Okay, so for version 4, we have h being defined for all x is not equal to 0, and h of 4 is negative 3. So when they say h of 4 is negative 3, what that means is that 4 comma negative 3 is on the graph of h. Sometimes they'll give you this, sometimes they'll give you this, but these are the same thing. And the derivative of h is given by h prime of x is x squared minus 2 over x for all x is not equal to 0. So in part A, we need to find all values of x for which the graph of h has a horizontal tangent. So the horizontal tangent means that the derivative is equal to 0. So since they're giving us the derivative, if we find out where the derivative is equal to 0, that'll give us all the values where x has a horizontal tangent. So let's do that. X squared minus 2 over x equals 0. And if we solve this, we're going to get x is equal to, well, we get x squared is equal to 2, and then x is equal to plus or minus square root of 2. So these are the two values. So x is equal to negative square root of 2, and x is equal to positive square root of 2. These are the two values where the function has a horizontal tangent. And now we need to determine whether it's a local maximum or a local minimum. And the way we're going to do that is we're going to look at all the critical points now, not just the where h has a horizontal tangent. So to look at all the critical points, we need to look at when the derivative is either 0 or undefined. So if we look at the critical numbers, that's going to be where the derivative is 0. So x is equal to square root of 2, x is equal to negative square root of 2, and where the derivative is undefined. Remember, it's not defined for x is equal to 0. So these are the critical numbers. And then now what I can do is I can set up a number line to check my signs for my derivative. So if you put the critical numbers in order, and then test for signs. So if I plug in a number less than square root of 2 into f prime, or h prime, I'm going to get a negative number. If I plug in a number between negative square root of 2 and 0, for example negative 1, I'll get a positive value. Here I'll get a negative value, and here I'll get a positive value. So notice that for both of my horizontal tangents, the derivative goes from negative to positive. See, at negative square root of 2 and at positive square root of 2. So what that means is that both of these values are local minima, because the derivative is originally decreasing, or the function is originally decreasing, and then the function switches to increasing. So this point here is a local minima. So what we will say now is there's a local minima at x is equal to negative square root of 2 and at positive square root of 2, because the function has a negative derivative, so the function switches from a negative derivative to a positive derivative at each of those values, or the function switches from decreasing to increasing at each of those values. For points, you get 1 point for finding that the two horizontal tangents are negative and positive square root of 2, another point for dealing with the fact that the function is not continuous at x equals 0, and therefore it is a critical point. And you get the third point for a proper explanation involving the derivative. Okay, now let's erase this and look at part B. Okay, so part B, on what intervals, if any, is the graph of h concave up? Justify your answer. So concave up, you should know that concave up means the derivative is increasing. So concave up, what that means is that the derivative, or I keep writing f because we usually use f, h prime of x is increasing, or another way to say that is h double prime of x is positive. So what we're going to do is we're going to take the derivative of this to get h double prime of x and find out on which intervals that second derivative is positive. Okay, so h double prime of x is, and now we're going to use the quotient rule here. So we're going to have x times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. If I simplify this a bit, I'll get 2x squared minus x squared plus 2 over x squared, which is x squared plus 2 over x squared. And now, for what values of x is this second derivative positive? And if you think about it, you'll realize that it's always positive no matter what value of x you put in. Even if you put in a negative value, it's being squared in both cases, so it's going to become a positive number no matter what. And since everything else in the function is positive, h double prime of x will always be positive. So h prime of x is always going to be increasing, so h of x is always going to be concave up. It's really important to be able to go back and forth between the first derivative, second derivative, the original function, and be able to know that if this is positive, oh, then that means h prime of x is increasing, and that means that h prime of x is concave up. Being able to switch between those. So that was that, and then you'd write down now h of x is concave up for all x is not equal to 0, because remember, it's still not defined at x equals 0. Okay, and then for points, get 1 point for taking the second derivative successfully, another point for showing that it's always greater than 0, and then a third point for the explanation that states that h is always concave up. Okay, now let's look at the next part. Okay, so write the equation for the tangent line of h at x equals 4. So whenever you need to write a tangent line, a good thing to do is to just write point and slope. So, because these are the two things you're going to need when you want to write the equation for the tangent line. You want a point, and you're going to want the slope. So at x equals 4, what's a point? It's going to be 4 comma something, right? Well, we know that there's 4 comma negative 3 is on the graph. So that's going to be our point, 4 comma negative 3. And then we want the slope of this tangent line. And that's going to be the derivative, right? That's what the derivative is. It's the slope of the tangent line. So at x equals 4, the slope of the tangent line is given by h prime of x, like that. So the slope is going to be h prime of 4, because we're doing it at x equals 4. So plugging in 4 into our h prime of x graph, we're going to get 4 squared is 16 minus 2 over 4, like that, which is 14 over 4. Okay, and then now that we have our point and we have our slope, we can write our point slope form, which remember is y minus y1 equals m times x minus x1. So we have our point, we have our slope, or m. Now it's a matter of plugging in the numbers. So y minus negative 3, so y plus 3 is 14 over 4 times x minus 4. Notice how I didn't simplify the 14 over 4 because it's not necessary. It's numerically equivalent, so we'll get full credit. And that is the slope of the tangent line, or sorry, that is the equation for the tangent line of the graph of h at x equals 4. So for points, this is just a quick 1-point question. You get 1 point for getting the correct equation. Okay, so does the line to the graph of h at x equals 4 lie above or below the graph of h for x is greater than 4? Why? So this question might seem a little bit off at first, because like, well, we don't know anything about what the graph of h looks like. Do we want to take the integral of h of x and graph it and then see what that looks like? No. That's way too complicated for this. All we need to do is think about the concavity of h. So if I just drew a general, like a stereotypical concave up graph, where it's increasing faster and faster, and I drew the tangent line at a random point, it can be any point. Notice that how the graph and its tangent line, the tangent line is below the graph. And I could have chosen any point along this graph, the tangent line would always lie below the graph. And then the same thing would apply if I drew a concave down graph like so. Anywhere I choose along this, if I choose, let's say this point, and I draw my tangent line, the tangent line is going to be on top of the graph. So what we've determined here is if it's concave up, then the tangent line is below, and if it's concave down, then it's above. So in our case, we need to figure out whether h is concave up or concave down at x equals 4. Well, remember how we said that in part B, h is concave up for all x is not equal to 0, right? So since h is always concave up, we're going to be in this section. So the tangent line is going to be below the graph. So your explanation would be, since h is concave up, and then just to be safe, you can write concave up for x is greater than 4, even though we know it's concave up for all x is not equal to 0. So since h is concave up for x is greater than 4, the tangent line is below the graph at x equals 4. Right? Let's move on to the next question now. Okay, question 5. It seems like it only has 2 parts, which is pretty cool. I guess that means less work, right? So we have a cubic polynomial function f being defined by this stuff here, and it's like immediately you're like, wait. There's like 5 different things here. There's an x, there's an a, there's a b, there's a k. What's going on? And it's like, oh, a, b, and k are constants. So we're not in like 5 variable calculus right now. That's good. And then the function f has a local minimum at x equals -1 and a point of inflection at x equals -2. So on the test, when you see local minimum or local maximum, what you should think of is the first derivative. And then when you see point of inflection or something relating to concavity, what you should think of is f double prime. Okay, so local minimum or extrema, that kind of thing, first derivative, point of inflection, something relating to concavity, second derivative at x equals -2. So since we're talking about both the local minimum and the point of inflection, we should probably take the first derivative and take the second derivative. Okay, so I'll take f prime of x, and thankfully it's just a simple polynomial function, so I don't really need to spend that much time on this. 2x plus b, and then I'll take the second derivative, since we're probably going to need to use that at some point, equals 24x plus 2a. And then now let's see what we have to do. So we know that at x equals -1, there's a local minimum. So if I plug in -1 into this, I'm going to get 0, right? So f prime of -1, which is 12 times -1 squared plus 2 times a times -1 plus b is 0, because there was a local minimum, the derivative is 0. And then there's a point of inflection, that means the second derivative is 0 when x is equal to -2. So if I take f double prime of -2, it's going to be 24 times -2 plus 2a, that's equal to 0. And now they want the values of a and b, and it seems like, well, look at this. We have this guy here. This looks like an equation that we could easily solve for a with, right? It's just one variable. So -48 plus 48 -48 plus 2a equals to 0. That means a is 24. And then what we can do now is we can take this value of a and plug it back into here, and that'll give us 12. I'll just take all this and we'll work a bit lower down here. So f prime of -1 is 12 times, well, -1 squared is just 1, so I'll just write 12 plus 2 times, and then our a was 24, right? So I can write 24 in place of a times -1 plus b is equal to 0. And now look, we only have one variable, so we can solve this for b. We'll get 12 minus 48 plus b equals 0. And then if we solve that, we're going to get b equals 36. That, and those are our two answers, because that's what they wanted, right? They wanted a and they wanted b. And then, so in terms of points, you get a lot of points. You get 1 point for taking the first derivative, 1 point for taking the second derivative, a third point for setting the first derivative equal to 0, a fourth point for finding the second derivative equal to 0, and then the fifth point for solving for the values of a and b, both. Alright, now looking at part b. So, if the integral from 0 to 1 of f of x dx is 32, what is the value of k? Okay, so, well, it's not immediately clear what we're supposed to do. So let's just take, we know that f of x is equal to this stuff, right? So let's just take that and plug it in for f of x and see what happens. So 0 to 1, and for f of x we'll put 4x cubed plus ax squared plus bx plus k. And then it's even like, this is the kind of time where like, even if it's not immediately like shouting out to you what the exact step should be, maybe it is, and that's great. But if it's not, just doing like simple straightforward steps, even if you don't get the right answer, you'll still net you some points just for trying and showing that you understand some stuff about calculus. So we can integrate this, and we're going to get x to the 4th plus 8. Okay, so in part b, if the integral from 0 to 1 of f of x is 32, what is the value of k? Alright, so this is the kind of problem, at least to me, where the way to do this doesn't pop out to you immediately. And in that case, the best strategy is to just do random stuff and hope you somehow find the answer, or even if you don't, you show the graders that you have understanding of calculus, and maybe it'll get some points, right? So we're integrating from 0 to 1 of f of x. F of x is this stuff here, right? So 4x cubed plus ax squared plus bx plus k. Remember we found the values of a and b in part a? So when I write f of x here, I'm going to replace f of x with this function and then plug in the values that we got for a and b. So 4x cubed plus 24x squared plus 36x plus k dx. And then we know that this is equal to 32. Alright, so now let's do the integration, and then we'll get x to the 4th plus 8x cubed plus 18x squared plus kx from 0 to 1 is equal to 32. And again, no plus c because this is a definite integral. And then if I plug in 1 into everything here, I'll get 1 plus 8 plus 18 plus k minus 0, 0, 0, 0, so that's it, equals 32. And then somehow we just did, straightforward steps, plugging in f, integrating, and somehow we suddenly got rid of all the fluff, and now we suddenly can solve for k. So k is 32 minus 18 minus 8 minus 1, and I'm not going to bother doing that because it's good enough. Okay, so we found the value of k, and in terms of points, that's going to be 2 points for this stuff here, 1 point for getting an equation in terms of k, and then 1 point for a numerically equivalent answer. Right? You don't have to simplify this down to 5. If you did, I mean, good, but I wouldn't recommend it. Alright, now let's move on to the final question. Okay, so question 6. Looks like we have a differential equation kind of question. And these are always great because they're usually really full of points for not a lot of work. So, we have a function f differentiable for all real numbers. The point 3, 1/4 is on the graph of f, and the slope is given by the differential equation there. So in part A, we need to find d squared y over dx squared. So basically they're telling us to take the derivative of this and evaluate it at the point 3, 1/4. So straightforward, we take the derivative of this and then plug in 3 for x and 1/4 for y, and then get a number out. So let's take this derivative, right? We're going to use the product rule, it looks like here. So if I take the derivative of 2y, I'm going to get 2y dy dx, because remember we're doing this implicitly, times 6 minus 2x plus y squared times -2. And then it seems like, well, hang on. How do we, we have a dy dx here. I can't plug in a number and get dy dx, can I? Well, we know that dy dx is y squared times 6 minus 2x, right? So I can take that and plug it in for my dy dx. So 2y times y squared times 6 minus 2x times 6 minus 2x plus y squared times -2. If you want to simplify this a bit to make your life easier, you can do that. You'll get 2y cubed times 6 minus 2x squared minus 2y squared, right? And again, this is d squared y over d squared, the second derivative. And then now what we want to do is we want to take this and we want to find d squared y over dx squared at the point 3, 1/4. So that's just going to be as simple as plugging in 3 for x and 1/4 for y into here. So that'll be 2 times, and then for y I'll plug in 1/4, 1/4 cubed times 6 minus 2 times 3 squared minus 2 times 1/4 squared, like that. And that is our second derivative. You don't have to, I know this evaluates, this whole thing comes out to 0, you'll just have this, but again, there's no point to waste your time on that. So this was a 3-point question. 2 points was for successfully taking the second derivative, and then 1 point for plugging in the point 3, 1/4 and getting a correct final answer. Part B, find y equals f of x by solving the differential equation dy dx is equal to that from our stuff there, with the initial condition f of 3 is equal to 1/4. So they just want us to solve the differential equation. Okay, and then remember that the only technique that you need to know for AP calculus is by separating the variables. So we're going to do that. So if I take the y's onto one side, I'll take the y squared, bring it over to this side. I'll take my dx, bring it over to this side. So while I have my y's on one side and my x's on the other. If I do that, I'll have 1 over y squared dy is 6 minus 2x dx. And then I can take the integral of both sides, and I'll get -1 over y. I'll move it down a bit. I'm really not going to go over the integration here. That's not really the main point. And by now you should know how to do that, I think. So -1 over y equals 6x minus x squared plus c. And I'm only going to include the plus c once, because when you do a differential equation, you only need to include a plus c once. Now I'll solve this equation for y, which isn't that difficult. I can divide everything by -1, so I'll get 1 over y is x squared minus 6x plus c. And then again, the negative doesn't apply to the plus c, because if you're taking a negative of a constant, it's still a constant. And then I can solve for y by taking the reciprocal of both sides. So I'll get y is equal to 1 over x squared minus 6x plus c. So the question is now, how do we solve for the value of c? Well, that's where the initial condition comes in. We have the initial condition f of 3 is 1/4. What that means is it's code for 3, 1/4. Right, so I can plug in 1/4 in here and 3 in here. So 1/4 is equal to 1 over 3 squared minus 6 times 3 plus c. So if I have this as an equation, I'll have 9 minus 18 plus c is equal to 4, which means that c is equal to 13. So now that c is equal to 13, I'll just take this equation here. Y is equal to 1 over x squared minus 6x plus 13. And that is my final answer. Because remember, they wanted y equals f of x, and we got that. So this question was worth 6 points. 1 point for separating the variables, 1 point for integrating y, 1 point for integrating x, 1 point for including a plus c in your problem, 1 point for using the initial condition, like we did here by plugging in the 1/4 and the 3, and then 1 point for solving for y and having it in this form by plugging in c again. Okay, so that was a culmination of the 2001 AB Calculus exam. I hope you found this video helpful, and I will see you in the next one. Goodbye.